Hey, I'm Stefan, the organizer and host of the embo++, the next level conference for embedded software developers. The talk you're about to see is given by Nino Vidovic. At embo 2021, he showed how to save resources with your toolchain. And thanks to Leica Geosystems, you can check out this talk online for free now.
Think I'm on air, right? Okay, so with my name is Nino Vidovic. I'm one of Zeger's embedded engineers, and today I want to talk about every byte counts, how a toolchain saves resources. We also have a little booth here on the EMBO, so feel free to drop in at any time. Usually me or my colleague Till Stork will stand there and be there for your questions. But you can, of course, just grab us to the side and talk about any topic. That's why we're all here to have fun, to learn things. So, yeah, let's get started with this one. So, what will this talk be about? So, we will first talk about what essentially a toolchain is, what the role of it is. Then we will look at what actually happens on a startup on a MCU and how all these toolchain elements play together to create the nice code you have at the output. Um, then I will show you three examples how this applies to applications that you might run into in your real life, um, and how this can create even smaller, faster, and better code. And at the end, we will, of course, have a little conclusion. So let's first talk about the toolchain itself and its main components. So uh, main components, I would say, are the compiler, linker, and assembler, where the compiler usually takes your C or C++ code and optimizes it where possible and translates it to assembler code, which then again uh, translated by the assembler then to machine code, and you have code that your target device understands. And ideally, it's small and fast, and so your embedded resources are used particularly well. Um, One sec. I'm hearing some echo actually. It's better now, I think. Okay. So yeah, and the linker essentially takes all the compiled files and places them at the at the memory you have specified and tries to, if possible, do this in a smart manner. Um, so with this smart optimization and the linker, for example, with code deduplication, you can reduce code size even further. Um, but let's talk about two additional components that are more or less um, not usually in the focus of toolchains, but um, are very important in this whole complex of a toolchain. And the first one is the runtime library for C and C++. Usually it provides you the basic functionality that the language standards implements, and you have all your programming language features in nice and uh, powerful functions like your memcopy, malloc, etc., and new for C++. Um, then we have the floating point library, which similarly to the runtime library provides additional components of your to your code base essentially, so you can have high level and low level mathematics. High level mathematics would be something like a sinus or cosinus functions, and low level math functions would be your addition, multiplication with floating point variables. And this library takes care of this in software. Of course, if you have a hardware floating point unit, your hardware takes care of this, so the code is already very small. But if you're running on the target device that does not have a hardware floating point unit, it's usually nice to have a great floating point library that has very fast and small code for your floating point operations. So the difference between a hardware and software implementation gets smaller, and you can still use your floating points. So all in all, this toolchain task is usually to create the smallest and or fastest code possible with whatever you throw at it. And but usually in this context, even if you look at commercial other commercial tool chains, they do not focus that much on the library part, which I think is they give away a lot of performance there, which we will be seeing later in my talk. And if you look, for example, the GCC and Neolibs, they usually they're pretty good, so you can work with them. They will do exactly what you need them to do, but they're usually not optimized in the best possible way for embedded targets as they could be. So this is where I think commercial IDs, the tool chains, sorry, can shine and improve codes for you. So this is also what our company has one focus on, is to provide such a tool chain, so you have also your small and fast code wherever possible. So to get a better understanding where we can improve our code and why toolchain where all the parts work together with each other well is important, let's talk about what happens on such an MCU startup. So this will be an exemplary startup for an ARM Cortex-M setup, but you can also the startup steps usually happen in a similar fashion on other architectures and target devices. So what I show here usually translates well also to other platforms, and we can learn the same things that we learn here for other platforms. So let me just switch quickly to my IDE. I have just to switch my sharing screen. So let's go to the IDE. So you should now see, yes, there it is. I hope you see it right. Yeah, this is this embedded studio I'm using for this example. And usually when you write your application, you write stuff in your main, either in C or C++. And this is where you add your code and functions. But we want to look at what happens before that. Well, why is this important, and what the toolchain can do here. And if we look at the entry point for Cortex-M is the reset handler. So we go here in the reset handler. So essentially, after the target resets, it will read read for boot from address 0 usually, and will read the stack pointer and PC where the reset handler is located, and it will jump to that location, and we end up here in code. And the first thing you see that happens, and don't be scared, I know this is assembler. Many people are scared of assembler. Don't worry, I will talk you through it and nothing will happen to you. So essentially the first thing that happens on any system is the system init. This is essentially the whole clock initialization and peripheral clock initialization, where you initialize external RAM, for example, and stuff like that. So everything that needs to be set up before your code can do its tasks. And if we look in this example, we used an STM32F4 as an example. So the system init will set some clock registers and those clock up the device to be in a desirable state to have your application run on it. And after this is finished, there is optionally a memory in it. So for example, as I said, if you have external RAM, for example, DDR RAM or stuff like that, it would be initialized here. This one, the vectors in RAM would be ARM specific feature where you can move your vector table. So let's not get into this, as this is core specific. This again, the vector table configuration is the same stuff, but here we are at floating points. So here we, for example, in this example, this target device has a floating point unit, so the corresponding registers for this target device are written and it's activated. But if we would use a soft device here, we would now use the code that would run that would come with your floating point library, which again it would run completely in software, and whenever you call do a multiplication or use a higher level mathematical function where floating points are involved, the library functions would be called. And after all this is finished, so we had the system initialization, memory initialization, floating point units, check if it's available or not, we start the runtime initialization. So we're still not at main, but we're getting there. The runtime initialization, this is where things like your data, your heap, your stack is initialized. But as you will see in a moment, this is very important here that the runtime library you're using and the startup file and the complete toolchain that you're using are fitting to each other. That is also why if you look at SDKs or other code bases from, for example, silicon vendors, if they provide you with startup code, they will usually have multiple versions for different tool chains. So it's always important to pick the correct one for yours. Here with you is, of course, our IDE. We will give you the correct startup that you need with this IDE. But if you take a look here, we let the linker essentially do some optimization already here, where the linker dynamically adds the needed initialization functions. So usually at this point, you would see, for example, a GCC runtime implementation, you would see a big block of startup code in assembler, which would do all this initialization stuff. For example, also the constructor calls for C++ objects. And this would be a very, very long block of code. We shorten this up here and essentially keep this nice and short, as the linker can dynamically place these functions as needed and create them. And if they're not needed, you save your memory, which is usually not the case with, for example, the GNU toolchain, where this is static and you would manually have to change your code so it gets smaller. So when this is done, we essentially have set up our target device, and we now can enter our app entry point, and this is usually your main function. And after this start function is called, we end up at main. So this would be a typical startup on a ARM Cortex-M target device. Let me just switch back to my presentation. There we go. So this is what happens in a startup. And you already saw, for example, how the linker can have a role here to reduce code size by linking it smartly by, so already your startup is smaller than if you do it in a static fashion. So let's get into the examples I talked about in the beginning. So our first challenge that we put in front of ourselves was essentially, okay, how small can we go? How small can we get in hello world? This is, I think, the de facto standard application that anybody writes in any programming language and tries to get running on any host or target system. So for reference, we took, for example, the Linux Hello World, which of course will use the GNU toolchain. And if you just use I think we did this with Ubuntu. And if you just compile your C code, where you just do a printf hello world, the resulting program will have 16 kilobytes roughly in size. This is a lot. I mean, we are talking about what's that, 10 chars that we want to print, and we have 16 kilobytes of code. Of course, this is unoptimized stuff like that, but still, uh, it's a lot of code. And if you would transfer this to an embedded target, you would roughly get the same size as if you use the GNU toolchain for embedded, as it's based on the same libraries and toolchain. So the reasons why this is so extremely, or one of the reasons why this is so big, is that we have, for example, the whole file system overhead. So fopen and for std out and std error are also implemented in this code, and some other corner cases, checks, and stuff like that that blow up this code to just simply print a hello world. And this is something that we don't really need or require on an embedded target device, as we usually use other interfaces to direct it as printf stream. And yeah, this is what it's where it's also important again to have a library which has embedded systems in mind, and where the best is done to avoid having bloated code for something simple as a printf. So uh, for small of printf, for example, we used Zegger RTT as an I/O interface. Last year, I did a talk on this, also here on the embo++. The talk was called RTT, the better printf and more. You can look it up at the NerdForce YouTube channel, or in the other room where the reruns are running. So the talk will show up there as well. So feel free to drop in. But all in all, the RTT interface is an I/O interface, so you can send data out and in, for example, for printf out. And in this case, without any optimizations, it's already just 1.7 kilobytes in size. And it's only that big because it has the target side printf formatter, so the whole formatting of the string is done on target side. But you already see we have a tenfold decrease in code size by just using software that's meant for you to be used on embedded systems. And the next question is, can we go even lower? And the answer is, of course, yes. So our solution here is host side formatting. So why should our target device do formatting of your string? It's just data, so let it be data. So just output the data and let the host handle whatever the data means. And this is also what a toolchain can offer. So in our case, it does, where you can simply switch between different supported I/O channels that are natively supported, which bring different benefits. In this case, it will be code size, because the resulting code for the same hello world that we used initially is suddenly just 281 bytes. If you do some further optimizations in the startup code, etc., it will be even 117 bytes, which I'll talk on my next slide. But all in all, you see that already by focusing on what target device you're running on thinking in this resource environment where you're operating in with an embedded target system, you can already achieve a lot by just using the right tools for the right task. So let's get to my other sample. Oh yeah, before I go to the other sample, we have we talk about this smallest hello world implementation on our blog as well. So feel free to drop in. You can either use this link or just Google Zegger and then every byte counts. So this is also a blog series that we did that shows different such challenges that we put up to our own toolchain and said, okay, how do we compare to others, and how can we do the go do the maximum for best code size and code and speed. So yeah, let's go to the next challenge. So let's talk about Blinkies. So blinking LEDs, which is, I believe, the de facto embedded target pendant to hello world, right? So the first thing you do on any embedded target is, okay, can I toggle a GPIO? Yes, I can. Great, I have control over my system. So that was our idea, is to say, okay, we have this target platform, again a Cortex-M, which is our trace reference board based on a STM32F4. Here you see it, and again for the setup, we used the Zegger IDE, the Embed Studio, and the toolchain that's included. And we started off pretty small already. So if you just compile the default startup code with the default main and just add the couple of functions that you need to set the toggle registers of this particular target device, we already were at 190 bytes. So this was already small, but the slide topic says that it's 100 bytes Blinky challenge. So we were like, okay, how can we go even further? So we were taking a look at exactly at what's the minimum you need to get such a target device up and running to still have workable code. So we really went to the max there. So this would maybe not be exactly a real world scenario because we threw out the whole interrupt handler. So we essentially limited the initialization to have only the things initialized to just get this LED blinking, and the end result was really impressive, and it was less than 100 bytes. I think it was 97 or 98 bytes. Again, you can look it up on our blog. I think this is very impressive. Looking especially on all these hardware extraction libraries that you usually get from silicon vendors, which are crazy big. So this same application that we have here, even with no proper system initialization, can easily have a couple of kilobytes in size without doing anything more than just blinking an LED. And this is extremely wasteful. And yeah, this blog article essentially takes it to the maximum and shows you, okay, what's the minimum I really need to have a target system up and running. The last challenge that I want to talk about here that we took upon ourselves is, okay, how can I have whole software floating point library implemented with all the standard operations like addition, subtraction, multiplication, and division, while still being IEEE 754 compliant. So this is a standard that defines how accurate your floating point results must be. There are even some commercial toolchains out there that do not meet this standard, which is a tough thing if you require to have reliable code and it doesn't meet the industry standards. So yeah, this was our challenge to say, okay, can we use all these functions and can we make it small? And again, we used the Zegger IDE and the floating point library, and the end result was actually, as a title.
Wir sind hier in einem kleineren Grossraumbüro.
Bei den Leitern habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Leica Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
Spoilered, it was less than 1 kilobyte. So, and this is especially important for such, let's say, low-level implementations for floating point functions for subtraction, multiplication, etc., because it's so easy to use in code where you don't think about it. So when you write code, you will just use these functions as because you need to calculate something, but you're not thinking about how much resources will this one operation take, because hey, some library will take care of it. And if this library doesn't do its best to have the smallest and fastest code, you're in trouble. So because for high level functions, you might notice it. For example, if you use a sinus or cosinus function, you're like, this is a complex calculation. Let's maybe not do it often. But the plus and minus, you will say, hey, this is so quick and simple. Why should this waste the resources? But with floating points, this can be tricky, especially in software, very quickly. And yeah, this is something our library also focuses on and does this, I think, very impressive job here. Again, you can read about it on our blog article for more details. We also have some articles on floating point face-off, where we essentially compare ourselves to some competitor floating point libraries and also the standard libraries from the GNU toolchain, for example. And the results are also quite impressive. So if you like to check it out, just Google for Zegger blog floating point face-off. There's 2 parts about it, and yeah, very interesting results. So if you use floating point functions in software a lot, this is something you might want to take a look at. So yeah, let's come to my conclusion. So as we all know, every embedded target has some kind of limited resource, either its speed, memory, or all of the above. And we want to use this resource as efficiently as possible. And we have to make sure, for us as tool providers, we have to make sure that this is that we do a good job, so you can write even better code. And this is why we think it's important to have a good partner here and a good software base that can be used. And let's not forget that any improvement you do in a C library, in the end, all C++ libraries you might use on top will profit from this. So if you call new, you will always use malloc in a C library. So if this malloc is small, your new will get smaller and faster. And so this is also something to always keep in mind. And it's always good if you have additionally to this tool chain some nice GUI and IDE where you can even understand your code much better and try to find places where you can chip off some more memory, for example, as we saw from the startup code before. So our toolchain, for example, is currently available for ARM targets and RISC-V architectures. And as a little teaser, maybe because we're here on the embo++, we might be working on a C++ variant where all this knowledge and implementation and improvements will also take impact in. So you would have your C++ standard library from Zegger, and I hope next year on embo++ I will be able to present it to you. So wish us luck, and I hope to see you next year as well. Thank you for your attention. If you have any questions, I think you can use the chat. If you don't want to use the chat or want to talk in person, no problem. I will be here on the embo this evening and the next 2 days as well, either at our Zegger stand or just running around. You can find me, just look for my name, Nino, and I think I'm the only Nino running around. If there are more, tell me. And yeah, that would be it. So do we have any questions? I don't see any in chat. So, there's one coming in. Where are we? Okay, the question is what kind of C++ library are we using as basis for ours for next year? I have unfortunately to say for now it's a secret, but if you keep your eyes and ears open and drop in our blog from time to time, this question might be answered soon. Any more questions? Okay. So another question is if we took a look at modern C++ features that could be used to allow the optimizer to throw away a floating point formatting if it is not used. So this is definitely something that we would be looking into. Right now, I can't say much about the process and progress. As I said, it's just a little teaser, so I will not go into any details. But you can expect that we will use our whole experience that we have accumulated over the last, I think it's now 27 years as a company to have to provide you the best possible software that you can use. Well, yes, it's particularly hard, but if it would be easy, everybody would do it, right? So. Right. If there are no further questions, I will step away from the podium now. As I said, I will hang out here for the next 1 or 2 hours. So just run up to me, ask your questions. Let's have a chat. Let's talk about embedded stuff in general. I'm happy to hear your feedback, what stuff you're using, what you're doing, what you're planning to do. And yeah, let's see what we can learn from each other. So thanks again and goodbye.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.